Hi, my students. This is the first lecture during the COVID-19 early days. This lecture deals with measures of variability. Measures of variability, also called measures of spread or measures of dispersion. Okay? Now, in the previous chapter, we studied the measures of central tendency and the measures of position. These measures fail to tell us the whole image about the distribution of dataset. Once we know the average of a set of quantitative data, our next question must be, how typical is the average value of all measurements in the data set? In other words, how spread out are the measurements about their average value? So these measures deals with the variation around the average value, the dispersion around the average value. Are the measurements highly variable and widely dispersed about the average value as depicted by the smooth relative frequency polygon, or do they exhibit high variability and cluster about the average value? The importance of looking beyond the average value is borne out by the fact that many persons make use of the concept of variability in everyday decision making, whether they compute a measure of the dispersion or spread. Because the measurements or the measures of central tendency don't reveal the whole picture of the distribution of dataset. Two datasets with the same mean may have completely different spreads. You see, the variation among the values of observations for one dataset may be much larger or smaller than for the other dataset. So we need a measure that can provide some information about the variation among the data values. The measures that help us learn about the spread or dispersion or variation of a data set are called the measures of dispersions. So this part of the chapter explains some measures of dispersion, for example, range, mean absolute deviation, variance, standard deviation, interquartile range, and semi-interquartile range, semi-standard deviation and semi-variance, and coefficient of variation. Number one, the range. What's the range? The simplest measure of dispersion or variability is the range. It's obtained by calculating the difference between the largest value and the smallest value in the data set. So although the range is the simplest and the easiest measure of dispersion, it's rarely used as the only measure of spread. The reason is that the range is based on only two values of the observations, and it's highly influenced by extreme values. Okay, this is the formula of computing the range. G equal LV minus SV, where LV is the largest value in the data set and SV is the smallest value of the data set. So the range depends only on two values, the largest one and the smallest one. Example number 1. The following data represents the scores of 8 students in statistics and investment mathematics. The first is stat, denoted by A, equal 12, 6, 10, 8, 14, 19, 7, and 18. Investment mass, denoted by B, equal 6, 14, 15, 18, 16, 17, 19, 18. Find the range for the two data and comment. Okay, by hand. For A, G equal the largest value minus smallest value. Here the largest value is 19 and the smallest value is 6. So range for A equal 19 minus 6 equal 13. And range for B is the same, equal 19 minus 6 equal 13. So the range is the same for the two courses. Okay? By MATLAB, we have a function called range. Range means the difference between the maximum value and the minimum value in the data set. So we can use the function range or the function max and function min. They means maximum and minimum value in the data set. Now enter the data like this. A equal 12, 6, and so on, and B equal 6, 14, 15, and so on. G for A equal range of A, range of A. So G for A is 13, and also G for B equal range of B equal 13. So the range is the same for the two data sets. We can also use the command max minus min for each course. Okay? The result will be the same. Number 2, interquartile and semi-interquartile range. Interquartile range, we studied it before, and equal Q3 minus Q1, the difference between the third quartile and the first quartile. And we explain this when dealing with the measures of position. Okay? As we discussed before, the interquartile range, denoted by IQR, is the difference between the third quartile and the first quartile. The semi-interquartile range defined as the interquartile range divided by 2. There are two measures of variability that overcomes the dependency on outliers or extreme values. Okay, so when the data are quantitative but contains some extreme values in one side or in the two sides, you have to use the semi-interquartile range as the measure of dispersion in this case, not the variance and not the standard deviation. Okay, so semi-interquartile range is used when the data set contains some extreme values or outliers, right? Semi-interquartile range denoted by SIQR equal IQR divided by 2, or Q3 minus Q1 divided by 2. Example 2. Find the semi-interquartile range for the following data. These data, solution by hand. First, we rank the data with ascending order from small to large. Okay, so this is the arranged data or the ranked data. Number 2, finding Q3 and Q1. Okay, so here the number of data 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We have 10 data. So R3 equal 10 multiplied by 3 divided by 4, Ni over K, Ni over K plus 1/2. So the range of R3 or the rank of R3 is 8. Okay, is 8. So Q3 equal the value number 8, number 8. So this is number 10, number 9, number 8. So Q3 equal 17. Okay, so you have to differentiate between the value of a measure, a position measure, or measure of position, and the rank of this position. The rank of Q3 is 8. Rank is 8, but the value is 17. But the same way, Q1 equal 10 multiplied by 1 divided by 4 plus 1/2. So the rank is 3. The value number 3. This is the value number 3, which equal 12. So Q1 equal 12 and Q3 equal 17. The difference between Q3 and Q1 equal 5. 17 minus 12 equal 5, and divided by 2, then the result is 2.5. Using MATLAB, put X equal the data set and SIQR equal IQR of X divided by 2. So we used here the function IQR, interquartile range, and we divide IQR by 2 to get the interquartile range. Number 3, the mean absolute deviation. Mean absolute deviations. متوسط الانحرافات المطلقة. As we see, both the range and interquartile range or semi-interquartile range depends upon two values, only two values only. Okay, so the range depends upon the largest value and the smallest value, but interquartile range and semi-interquartile range depends upon the third quartile and the first quartile. Okay, so each of them depends upon only two values in the data set, not all the values, only two values. Okay, and neglect the other values or the remainder of values in the data set. The range uses the largest and smallest value, where the interquartile and semi-interquartile range uses the first and the second quartiles. So these measures depend on some values only and not all values in the data set when describing the variability of the data. Okay? The mean absolute deviation is the measure of dispersion that use the absolute deviations between each value and the mean of the data, and compute the average of these absolute deviations as follows. ADB equal sigma x minus mu, the absolute value of the difference between x minus mu, over n for population. Okay, so this is the difference between every observation or each observation and the average of the population. Okay, but this difference, okay, of these differences computed by the absolute value. So we omit the sign, whether plus or minus. For a sample ADS, so ADB is absolute deviation for population. Absolute deviation for population. ADS is absolute deviation for sample. Okay? Equal sigma x minus x bar, the absolute value for the difference between x minus x bar divided by n for sample. Okay, this is the formula for computing the absolute deviation for population and for a sample. Example 3. Assume that the following data list the score of 6 students: 14, 14, 16, 20, 13, and 19. Find the mean absolute deviations. Okay, so to get the mean absolute deviations, we have to compute firstly the mean, the arithmetic mean, then compute the difference between every observation and the mean of the data set using the absolute value, not the value itself. By hand, first we compute the mean for sample as follow. X bar equal sigma x over n, so x bar equal the summation of x, which is 96 divided by the number of observation, which is 6. So x bar equal 16. So the average of the data set equal 16. Second, we calculate the mean absolute deviations as follow. This is x, and we computed x bar as 16, then x minus x bar with absolute value equal 14 minus 16 equal 2, 14 minus 16 equal 2, 16 minus 16 equal 0, 20 minus 16 equal 4, 13 minus 16 equal 3, and so on. The summation of x minus x bar equal 14. 2 plus 2 plus 4 plus 3 plus 3. So absolute deviation for a sample equal sigma x minus x bar with absolute value divided by n equal 14 divided 6 equal 2.33. By MATLAB, using the function MAD means mean absolute deviation, or function ABS, absolute deviations, and the mean we have. So it's preferred to use MAD instead of ABS and the mean. Okay, so the main function is MAD. So ADS equal MAD of x equal 2.33. Or you can use mean of ABS of x minus mean of x. Okay, again, mean means the average of the absolute values between x and the mean of x. So this is the summation, but using the ABS, not the value itself. Okay, so it's better to use the function MAD instead of ABS and the mean. Number 4, median absolute deviations. This measures uses the absolute deviation This measure uses the absolute deviations between each value and the median of that, not the mean, like mean absolute deviation. So the difference between mean absolute deviation and the median absolute deviation, we compute the deviation or the difference between each value and the mean in case of mean absolute deviation, and the difference between each value and the median in case of median absolute deviations. Okay, so this measure uses the absolute deviations between each value and the median of data, not the mean. Okay, and then compute the median of these absolute deviations. Okay, the median of these absolute deviations. Okay, so ADPM equal M of x minus m here median of the absolute deviation between x and m for population, or m of x minus m for sample, okay? So we have to get the median of the differences between each value and the median of data set for population, and the median of the absolute values for the differences between x and median of x for a sample. For a population, we say ADPM, AD absolute deviation for population median, and here absolute deviation for sample median, okay? Where m is the median of population, m capital, and m small is the median of a sample, and there is no difference in calculations of the way of calculating the mean absolute deviation or the median of absolute deviation is the same for a population and for a sample. Example number 4. Find the median absolute deviations for the data in example 3 by hand. First, we rank the data in ascending order as follows: 13, 14, 14, 16, 19, 20. Second, we compute the median as follows. Now look, here the number of data set is even number, 6. So the median is the value between the third and the fourth observation, So the median equal 14 plus 16 divided 2 equal 15, okay? Find the absolute deviation between each value and the median as follows. Now the median is 15, so the difference between each value and 15 will be x minus m, the absolute value between x and m. Each x, 13 minus 15 equal 2, 14 minus 15 equal 1, 14 minus 15 equal 1, 16 minus 15 equal 1, and 19 minus 15 equal 4, and 20 minus 15 equal 5. Okay, so these are the absolute deviations between each value and the median of data set. Okay, we have to rank these deviations, then get the median of the deviations. Rank the absolute deviations as 1, 1, 1, 2, 4, 5. We have 6 deviations, I mean even number. So the median will be the middle value between the third and the fourth deviations. So the median is 1 plus 2 divided 1 equal 1.5. By MATLAB, using the command mat x and 1. So the command mat of x means the mean absolute deviation, not the median. Mean absolute deviation. For median absolute deviation, use 1. Beside x, use 1. Okay? So, or you can use the functions median and abs like this. So these are the measurements or the data set denoted by X, and ADSM, the absolute deviation for the sample median, equal MAD X and 1. X and 1. So when putting 1, we mean median absolute deviation, not mean absolute deviations. So the result equal 1.5, or you can use median of abs of X minus median of X. Okay, but it's better to use MAD X and 1. MAD X and 1. So when using the MATLAB program, use MAD of X to compute the mean absolute deviation, and use MAD of X and 1 to compute the median absolute deviations. Number 5, variance and standard deviation. Variance and standard deviation are the two most widely used and accepted measures for the variability of the cardinal data set. Cardinal data set means the quantitative data. And also, I remember you that the quantitative data which not contains extreme values. So we use variance and standard deviation for quantitative data that is not contains extremes in one tail or in the two tails. Okay, remember this. They are closely related to each other. They take into account all the values in the data set. So the variance and standard deviation, like the mean absolute deviation and the median absolute deviation, depends closely or related to each other, and the same way depends upon all values in the data set. Okay? They based on the difference between the value of each observation and the mean. The difference between each value and the mean is called a deviation. A deviation about the mean. Okay? These deviations about the mean are squared when computing the variance. So the variance of population data is the average of these squared deviations. So what's the meaning of the variance of a population? The variance is the average of the squared deviations between each value and the mean of the data set. The value of variance and standard deviation tells us how closely the values of the data set are clustered around the average. Clustered means closed around or about the average. In general, a smaller value of variance or standard deviation indicates that the values of the data set are spread over a relatively smaller range around the mean. In contrast, a larger value of variance or standard deviation indicates that the values of the data set are spread over a relatively larger range around the mean. The standard deviation is the positive square root of the variance. The variance for population data is denoted by sigma square, and the variance for a sample is denoted by S square. Consequently, the standard deviation computed for population data set is denoted by sigma, and the standard deviation calculated for a sample is denoted by S. The sample standard deviation S is an estimator of the population standard deviation sigma, and the standard deviation of is either and interpret than is easier to interpret than the variance, because the standard deviation is measured in the same units as the data. Okay, so standard deviation is measured in the same units as the data, but using variance, the units will be squared, not looks like the units of the data set. The following formulas are used to compute the variance and the standard deviation for population and sample data. This is the first formula, as we said before. Here, sigma square is the average of the squared deviations between each value and the average, the squared deviation between each value and its average. Okay, and sigma, the standard deviation, equals the square root of the variance, right? Or the second formula is sigma squared equal n, sigma x squared minus sigma x all square over n square. Okay, here you can compute x square instead of x minus m square. Okay, so it's so easy. The second one, it's so easy from the first one. And s, the standard deviation, equals the square root of this variance. For example, s square equal sigma x minus x square over n minus 1, not over n. And s, the standard deviation for example, is the square root of the variance for example. The easiest or the simplest formula for computing the variance and the standard deviation for example is s squared equal n sigma x square minus sigma x all square over n multiplied by n minus 1, right? And the s equals the square root of the variance. Okay, so it's the simplest formula for variance and the simplest formula for the standard deviation if we deal with a sample data, not with a population data. Okay? Example number 5. The following data lists the age of 8 managers in a firm by years. Find the mean, variance, and the standard deviation for a population and a sample. Okay? Solution by hand, finding the mean. Okay, put x, and the x, the summation of x, equal 427. Then the number of x is 8. Then mu for population equals sigma x over n, and x bar also sigma x over n. So mu for population equal x bar for the sample, and each of them equal 53.3. The variance and the standard deviation for population, n sigma x square minus sigma x all square over n square. Okay, so sigma square equal 1.7, and sigma equal the square root of 1.7 equal 1.3. Then computing the variance and the standard deviation for example, s square equal 1.9. okay, so the variance for a sample is larger than the variance for population. Why? Because we divided by n minus 1, and for population we divided by n. Okay, so n square, here n multiplied by n minus 1. So the variance of a sample must be larger than the variance for population, and consequently the standard deviation of the sample is larger than the standard deviation for a population. Using MATLAB, now to compute the mean, use the function mean. So mean equal mean of x, and variance for population equal var x and 1. Variance for population equal var is a function to compute the variance. X and 1 is the variance for population, not a sample. Okay, and standard deviation for population equal STD. STD is a function for computing the standard deviation, also for x and 1. So for population use x and 1, whether using the var function to compute the variance or using the STD function to compute the standard deviation. Okay, remember that here for population add 1 to x, add 1 to x. Okay, var for a sample, the variance for a sample, use var of x, or sometimes var of x and 0, but it's better to use var of x for sample and var of x and 1 for population. For standard deviation for a sample, use STD of x, okay, like this. Okay, so the values using the MATLAB is the same as the values calculated by hand. Example 6. Suppose that the following table implies the positive profits and negative profits for fire insurance line during the past 10 years by million of Egyptian pounds. So here minus 9 means that the profits decreased by 9 million Egyptian pounds. Decreased. Here 11 means the profit is increased by 11 million Egyptian pounds, and so on. Compute the variance and the standard deviation manually, and using the MATLAB, and compute the population parameters with the sample statistics. The population parameters means the mean and standard deviation with the sample statistics. Okay, so these are the data set or the observations. The variance for a sample equal var of x, and the variance for population equal var of x and 1. Okay, so here the variance of a sample is greater than the variance of population. The standard deviation of a sample equal STD of x, and the standard deviation of the population is STD, X, and 1. But the same way, you see that the standard deviation for a sample is larger than the standard deviation for population. Manual solution. First, compute the mean for population and the sample. Okay? The summation of X equals 25 and the number of observation equal 10, then the mean is 25 divided 10 equal 2.5 million Egyptian profit, and sample observation size is 10. Okay, the following table are figures implies the calculations. Here, look, X transpose means explain X as one column, X minus mu transpose the deviations in the shape of column, X minus mu squared transpose as column also. This is the table. N equal 10 and the M equals sum of X divided N. So instead of computing by hand or computing by calculator, get the summation of X and divide by N. This is the mean for population. The variance for population equal sum of X minus M dot hat 2 means squared, dot hat 2 means squared, divided by N. Okay, X minus M is an array, so when getting the power 2 for an array, put dot and hat, for power 2. Variance for sample equal X minus M dot hat 2 divided N minus 1 not N. Okay, the standard deviation for a population equal SQRT. SQRT means the square root of variance for population equal 9.8, and the standard deviation for a sample equals the square root of variance for a sample. Okay, so these functions, instead of calculating by hand or by calculator, not using the function of var and standard deviation. Okay, semi-variance and semi-standard deviation. This is an important point to use one side of deviations instead of the two sides of deviations. Semi-standard deviation only measure the standard deviations of the downside deviations and ignores the upside fluctuations. Okay, the calculation of semi-standard deviation involve only the values below the threshold in case of profit, the values below the threshold may be the expected value or any other value. So the values below the threshold or the expected value means the negative profits. The negative profits. The profits which are less than the expected profit. Okay? Or the negative cash flows. Cash flow looks like profits, which is called the downside deviations. Okay? So the downside deviations means a decrease in cash flow or decrease in profit. Okay? Or sometimes called the risk. The risk. Okay? Or the values above the threshold in case of loss. In case of loss, we mean the positive losses, the losses which exceed the expected value or the threshold of loss, which is known as upside deviations or risk. Okay, so the risk for losses is different from the risk for cash flow or for profits, and the deviations for losses is called the upside deviations, but the deviations for cash flow or for profits is called downside deviations. Okay? Example 7. Find the semi-variance and the semi-standard deviation from the data involved in example 6 manually and using MATLAB, and compare the population with the sample computation. Here we will deal with the negative profits only using MATLAB. These are the negative profits. So these are the downsides deviation, not the upside deviation. The semi-variance equal var of x and 1, x1 and 1. So x1 means the downside deviations, the negative profits, and for a sample the variance equal var of x1. You see that the variance for population is less than the variance for the sample, and the semi-standard deviation for population equal STD x1 and 1 equal 1.4, and semi-standard deviation for a sample is STD for x1, which equal 1.58. So also the semi-standard deviation for a sample is larger than the semi-standard deviation for a population, and the semi-variance for a sample is larger than the semi-variance for a population. Manual solution. Manual solution, put a table on this, x1 transpose, put x1 in a column, x1 minus m1, the difference between each value and the mean, this one, and the squared differences between x1 and the mean, this column. Then compute first the mean equals sum of n1 divided n1. Variance for population equals sum of x minus m1 squared divided n1. Okay, so instead of calculating by hand or by calculator, you can use the MATLAB program as a calculator, not using the function. Okay, so variance for sample equal sum of x minus 1 squared divided n1 minus 1, and so on. A standard deviation or semi-standard deviation for a population equal square root of variance or square root of sum x minus x1 minus m1 squared divided n1, and semi-standard deviation for a sample equal square root for variance or sum x1 minus m1 squared divided n1 minus 1. Okay, so now we finished this lecture, and we have two measures of variability. They are the coefficient of variation and what we call the box plot, which we explained in the next lecture. Goodwin. Thanks.